Alright, so welcome everyone. Welcome everybody watching the video. It's great to have you here. I am Adam and we are going to learn Godot, I guess. This is my first time doing this, so I'm I'm not expecting myself to be super professional, but I will try my best to cover everything that's important in game dev and like all that stuff, I guess. So we have this Discord server here, which I encourage you to join too, because we have a lot of rooms for news, some polls, and the actual schedule. This is what we're gonna go through in the first lesson. So this is just an introduction to game dev, basically, as well as programming and some game engine theory. So like you understand what's happening under the hood, and like that just makes your work more efficient, I believe, if you know what's happening and you're not just typing the code and like trial and erroring your way through. So yeah, okay. So first of all, I'm going to I'm gonna have to share my entire screen here. There we go. And we're gonna look at installing Godot in the first place, because Godot engine is the thing we are gonna be working with. Okay, yeah, let me just close this. So installing Godot, as you may have figured, is quite simple. You just type in Godot, but hang on, because if you head to godoengine.org, here's this download latest, which is Godot 4.1.1, and that's what we need. We don't need the LTS version, because this is 3.5. This is basically the stable version of Godot. I mean, 4.x is already stable as well, but 3 is just the more complete version. So if you click download latest, that's just going to take you to this page, and you'll be able to install Godot engine. Here's also this one for .NET, which has like C# support. C# is another programming language you can use, but we will be using Godot's built-in language. So now we're gonna get this zip file, and you can unzip it if you want to. You can just use this exe file actually. And so, as you may have figured, these two are identical almost by the file name. So if you open these, you see here Godot opens with a console log, which can be helpful for troubleshooting, but really it's not that like required, I would say, to launch with that. So anyway, you just click on this, you start this 4.1.1. Actually, I think I have 4.1.0 installed. Yeah. Doesn't really matter, like there are tiny differences. So if you launch this, the project manager is going to pop up, and this lists all your projects. You can also download stuff from the asset library, which is like a collection of pre-made assets or scenes or projects, however you want to call them. And we will actually get this a bit later on. So if you want to create a new project, you just click here, new project. You can name it. I'm just gonna name it. Oh, yeah, sorry, my keyboard is placed on its cable because I put it up on the desk for my drawing pad to fit. So like that's gonna be inconvenient. Okay, I just fixed it. Cool. So I'm gonna create this folder. For render, you just want to keep everything as it is here. And then create and edit. Now it is going to load. All right, so this is the interface we'll be primarily working with, but before actually being able to do anything, we will need to understand some some theoretical information about game development and programming as a whole. So I'm just going to copy these things over to Paint and we can talk about them. How's that? Okay. This is just a lot to go through. I don't know where to begin, to be honest. Okay. I think I got it. So imagine a game where you have the screen. That's not the best rectangle I've ever drawn. I'm probably just gonna use this. Okay. So imagine a game where you have your screen and then you have a character with a gun shooting other people. The body should be a bit more curved like this, but doesn't matter. We're shooting the people. So how can that happen? And then also there's a map, right? Let's say this is a crosswalk. The characters are on the street. Okay. And you have a UI for like health. And also your ammo. So for people with some knowledge on games or like programming, it would probably be obvious, but if I were to ask you how you would store your HP or how it appears on the screen, what would you say? What data is that? What data is the number 50 on the screen? And on the screen is pretty important because it's not just text. It's not only text data. All right? It's not just text. So it has font, right? It has color. It has obviously the actual text data that we would display. And then like there are a bunch of other options. Oh yeah, I'm going to pause this. Close it, sorry. Okay. And this is not all. So if I open Godot, you don't need to understand what I'm looking up right now. But if I were to place a text label that can display 50 on the screen, you can just right here follow my cursor. So you can see all the options this text has, and this is not all. You can also like open these drop downs. There's just a lot. There's also position, scale, rotation. So yeah, it's not just the text of 50. It consists of so much more. And also you have to consider that this is placed on the so-called user interface, which is not the game world. This is all UI or user interface. And we call it that because it's the interface of the game and it's above the game world, if that makes sense. In the game world though, here's the character, here's the street, here's the crosswalk, right? It's basically the thing where game action happens, and the UI just shows relevant information about that. So we have the UI and the, well, in our case, the 2D world, right? I guess this is obvious to some people, but like if you're completely new to game dev, this is actually going to be pretty important because there's a huge difference between UI and just the 2D world. In Godot, we call uh, never mind, we'll get into that later. Okay, so here are those layers. How do we display these, right? Because, yeah, you just place some textures on the screen, but a game engine, which is Godot, consists of several parts, which again might be obvious, but the most important part, one of the most important parts, is the renderer. If you ever heard of OpenGL or Vulkan, those are renderer APIs. And API means Application Programming Interface, which is basically a how do I phrase it? An API is a group of functionalities that you can use. It's like a third-party thing in a system, I guess. That's a good way to put it. But anyway, so in the game engine, you have the renderer, you have the physics engine too. Physics are also very important. And then there's just a lot of things going on. And you don't necessarily need to know about these in detail. And I could go into rendering a lot deeper. I don't think there's a need for that right now, because I would rather emphasize programming theory, which I'll get into in a minute. But yeah, game engines are pretty complex, and like that's the reason why like not too many people make them, right? It's pretty time consuming. Back in the 90s, there weren't freely available game engines. Like you couldn't just go ahead and use Godot. You had to write your own renderer, your own physics, your own audio system, everything, and that's tough. Okay, so let's get into the programming side of things, I guess. And we won't be doing practical programming right off the bat. We will just look at some programming theory, which might be boring, but you will probably thank me later. So, if I were to show you some code, like, I guess I can. So here's this code, right, that we can write. I could type anything here, anything what I want. So, how does the engine understand that? Well, to begin with, Godot uses its own language called GD script. So if you see the GD file extension, that's what it means. And it is sort of similar to Python as well, if you've ever heard of the Python programming language. They're quite similar, but not really the same. So, how, so how does the computer understand what we want to do? There are a lot of steps before that. So we just write the code, right? Write GD script. And then when we click play, you can launch a project by pressing F5 or this button. You will need to assign a scene, but like, yeah, we'll get into that later. So when you start the game, right, Godot interprets the code. It interprets it. And that's the actual technical expression. It is pretty important to get the difference between interpreting and compiling. But yeah, so it is interpreted by Godot, right? And you need to know that Godot was written in a different language. It wasn't written in GD script. It is only interpreting GD script. Godot is written in C++, which is a fairly low-level language compared to today's standards. Okay. I just checked on the Discord because I was paranoid that you guys pinged me because something is wrong. Anyway, so Godot interprets the GD script code we write, and there are Godot interprets the GD script code, and so it has to, Godot is written in C++, so it cannot, the code we write in GD script cannot operate as it is. So Godot needs to translate the GD script expressions so that it can operate in C++, the language it was written in. So let's assume that, okay, Godot was written, yeah, it's using C++, but in GD script, we told Godot that we want to shoot the enemy, right? There's actually a long process, so let's just say we want to spawn a sprite here, or a human character. We just want him to be there. And Godot will have to interpret that GD script command in C++, which means it needs to parse the expression and the instructions of just doing this. There are built-in functionalities in GD script that are like shorthands to like the C++ equivalents, and basically every built-in functionality in Godot is like translated to C++ in a way, because if you say that here's a character sprite, a texture, if you may, if you want to if we want to, let's say if we want to delete it, then Godot just sees that we want to delete the texture, and it will do the C++ equivalent of the deletion, right? Let's go a layer deeper, shall we? So we'll just discuss this, how GD script becomes C++, blah, blah, blah. But the machine still can't understand C++. That is still a language we use to be able to work faster. So the machine, our PCs, understand machine code, which is, as you may guess, zeros and ones. So yeah, this may sound strange, right? But at the lowest level, this is what code you write is like. It's just a million zeros and ones. It's binary code. This is in the binary number system. And the number system we use for like our daily lives is the decimal system, which has 10 digits, right? It goes 0 to 9. Binary is 0 to 1. And that's it, because ultimately the machine only understands on and off as the two states, right? And we can just do so much using these two states. It is pretty incredible. So let's fast forward a bit. So what happens with C++? It becomes assembly code first. It becomes assembly code, and assembly is the lowest level programming language that exists. And yes, it was written in machine code. Like yeah, it is just pretty hard to fathom that an entire thing like this was written in machine code. I can show you some assembly. It's not gonna be your average programming code snippet. Let me show you. This is what assembly is. It actually has very primitive instructions. So it does things like move, add, divide, multiply, subtract. You can see mov is move. Add is addition, of course. And it is using registers and these weird numbers. What could 0x3c be? We are going to get into that as well. But so the fascinating thing about assembly is the instruction kit. Instruction kit for programming, and any code, literally any code you write, no matter how complex it is, it consists of assembly's instructions. Like, yeah. That's really all it is. It's just a bunch of simple instructions. You know, when you face a complex issue and you like try to break it down to smaller parts, and that's basically the situation with programming. Like, even when you're thinking about how to solve the problem, and even that's what the compiler is doing, right? The compiler, now that I've just said it. Oops. The compiler is the architecture that converts C++ to be assembly code. And the compiler does a lot of things. It has to do syntax checking, right? So you cannot just type whatever you want. You need to follow a syntax. Same thing with speaking language, right? I can't mix words because it won't make sense to the listener. The listener may be able to tell what I'm saying, but if the compiler was to make suggestions, that might just end up being incorrect and a waste of resources. So yeah, there's a lot the compiler is doing, and it also does optimization. So if you were to type, I'm going to type this in assembly, like pretty basically. If you were to type add 5 and 8, and then you wanted to subtract wait, that's not how I'm going to do it. So let's assume x equals 5. Okay. We have a data named x, which equals 5. Let's assume I want to add 8 to x. And then I want to subtract 3 from x. So, how, the compiler is able to optimize this into one set of instructions. So this becomes add x5, right? Because if you add 8 to x, that's 13, and then if you subtract 3, it's 10. And oh look, it's the same thing with this. 5 plus 5 is 10, right? This is just pretty basic things, guys, to like give you an understanding of how compiler optimization works. But yeah, this is basically what the compiler also does, and it does many things, but I don't think I'm qualified enough to teach you in more detail. So I won't spread misinformation. Let's just agree in that. And yeah, so I mentioned this weird series of numbers and digits. So this is a memory address, 0x3c. However, this is not binary format. This is hexadecimal. Which has 16 digits. So it goes from 0 to 15, right? But hey, hang on. If I were to type two numbers, let's say I'm typing this in hexadecimal. Is this 011 or 011, right? We cannot have numbers with more than one digit because that will lead to confusion. So what people figured out was that we could use 0 to 9 and A to B, C, D, E, F, because this is 6 digits. Besides the 10 we already have. Okay, I'm going to give you a quick crash course on how to calculate binary and hexadecimal, and you're free to just really look this up on your own too, because it may take a few numbers to like get the hang of it, but this is not super important either. So yeah, that's why I'm not going to go into detail, but it is interesting, and like you'll eventually like probably get around this one way or another if you're doing some advanced stuff. So if I were to convert 24 to binary, how would I do it? Well, okay, so this is 24 in binary. The way we convert is that each placement of digit has the power of 2 assigned. The first digit from the right has 2 on the 0th, which is 1, by the way. This is 2 on the first, 2 on the second, 2 on the third, 2 on the fourth. So this is 2, right? 2 on the first level is 2. This is going to be confusing. Okay, this is 4. This is 8. And this is 16. So you may get it by now, but if if the digit in binary is 1, then you add the corresponding power of 2 to the number overall. So because 24 equals 16 plus 8, the digits of the fifth and fourth digit are ones. And wherever you have a 1, you add the numbers. So there you go. And same thing for hexadecimal things, hexadecimal numbers, except it's 16 on the 0th, 16 on the 1st, and so on. You can do this with any number systems, by the way. It works if you have free available numbers, you know. It works with any amount of numbers in any number systems. The logic is the same. So the interesting thing about this is that memory addresses are stored using hexadecimal. You can see it here as well, or here. And memory access is actually going to be important in the next lesson, because we will look at referencing memory. Because you have RAM in your computer, right? And that's the place where data is stored, temporary data, basically program data, whatever we compute in code. So the text data, the text color, and so on. They are laid out. Typically, every program has a designated area of memory that it can use. So, like, if you have your RAM, let's say you have all these slots and space. If you have your game, ideally, the game's data is gonna be grouped so that they are next by each other. And if you have Firefox here, your game would ideally not be placed so that its space continues here. So if this is the first section, right? This is second, third, fourth, fifth, sixth, seventh, eighth, ninth, and the 10th. So if Firefox is here, your game would ideally be positioned so that it's here and here, and also here if it takes 3 so-called sections. But yeah, this is just the tiny details of accessing data. There are situations where you are referring to already stored data. So let's say you want to store the number 6, right? You store it, it's going to be in the memory, cool. But what if you want to store a texture? A texture could be, well, this is actually going to the VRAM, but like, let's assume the VRAM and the RAM are united now. VRAM stands for video RAM, and also if you run out of video RAM, which is like a part of your GPU in a way, then RAM will be used anyways. And this is just for the sake of demonstration. So if you want to store a texture for your game, and you store it in runtime, runtime means when your program is already running, right? Its information gets into the RAM. But what if you have a character or a character texture or sorry, yeah, what if you have a character and you want it to have this texture in particular, right? And what if you have another character and another and so on? So that would mean you would need to load the texture as many times as a character exists. You would need to have it stored all the time. Or if you have a resource, right, like a font. Font information is also the same as a texture and it's a better real-life demonstration. But for the sake of simplicity, let's just stick to this example. So if the texture is stored here, right, it takes a couple of space. It's just sitting there, and we can actually refer to memory addresses. So remember how I just said this is the first place, the second, the third? They have addresses in hexadecimal format. You could say this is 00, this is 01, and so on. I'm going to continue this for the sake of showing you that this is first, second, 0, 01, 02, 03, 04, 5, 6, 7, 8, 9. And then what? Then 0A, right? So we can do this cool thing called referencing data by knowing the memory address. In C++, you can actually do that by programming. You cannot do it in Godot or like most high-level languages. But we call these pointers. So you can assume a pointer exists in memory. A pointer that points to the memory data of texture, which is at 0x08. Wait, I'm dumb. 7. And so now we don't need to have the texture stored in the memory a million times because we have a pointer that points to it. And that will just show us the location of the texture, which means now a pointer, typically the size of a pointer depends on the operating system and whatever architecture you have, either 32-bit or 64-bit ones, but let's assume this is 32 bits, 4 bytes, right? Because 1 byte is 8 bits. Now we have the texture which can, yeah, so another amazing thing about pointers is that the texture could be 10 megabytes, but the pointer would still be 4 bytes because what the pointer restores is the address and not the actual data that it points to. A pointer doesn't know what it's pointing at. So yeah, this is pointers for you. They are actually insanely useful. We will see them a lot actually while while programming, even though we cannot create, well, in a way we can create pointers because here's this thing called reference based data. And here's the opposite, the value-based, right? It's the number, and then the reference-based is the texture. Okay. Okay, let's look at resource management a bit. So, what's a resource? It's anything that we really store, except like scripts, you know. A resource is a thing that's stored in your game project. It can be a texture, a collection of data, right? Like a item in your inventory, an item type to be specific. Or it could be scene information, or scene files, or level files. Level is more of a gamer terminology. So developers call levels scenes more often than just levels. And if I open Godot, so this is our file system. This shows us the project directory. You can see we have this icon by default. And this is also a resource, see? Here it says resource. Even though this is a texture, everything, or like most things, inherit from resource. Can I? Oh yeah. So if you want to create something new, first of all, this res colon slash slash, this is your root of the project directory. If I open this in File Manager, you will see I land in the project directory, and basically whatever's displayed here is what's compatible with Godot and is here. You can see here's the icon, right? The thing we are literally looking at from the editor. And here's our project.godot file, which is just some project information. This is also parsed by the Godot editor. So if I were to change anything here, or from even the project settings, this file would get updated. This is a form of parsing where like the engine interprets whatever we say here, right? You can see here's a syntax. It is even explained here. You could basically take this as a interpreter, the same way Godot interprets GD script, but this is much more simplistic, of course, because this just stores settings. So anyway, this res colon slash slash is the root of your project. And if you right click and go to create new, you can create many things. Here's a folder, a scene, a script, a text file separately, and a resource. You see there are a lot of resource types. We have animations, light related stuff, collisions, audio, and just really many things. These are all resources. And Godot needs to load all of them, which is a lot of work. Okay. So let's talk about the execution flow. What does that mean? execution. It means the way the game operates or handles a series of events. You see, if you start the game, something needs to happen at the start. Something needs to happen every moment. Something needs to happen when you do an input or when you quit the game, right? So in Godot at least, there are many so-called functions we have for separate parts of a object's lifecycle or the game itself. We have init, which is called when the object is created. Maybe we should talk about the scene tree first before really going into the execution. All right. Sorry for that. Scene tree. What is a scene tree? Hang on, let me do this. Okay. So you may have heard of the tree structure in programming. Right? These things. This is how information in a scene is stored. You know, a scene can either be a level or just a separate object even. It is up to how you interpret and handle them. Okay, so now you can say it says scene. This is the scene I've just created. And if I add some other things, or if I just copy this, you can say a little tree drawing out, right? This is the root node, the root of the tree. And then you can see we have two direct children, these two labels. And they have other children as well. This is how we call them. So controls children are basically all the labels. Oops. Yeah. And its direct children, however, are this label and this label. Alright. And so if you, for example, if you had two characters on a level, there would be a root, right? And that would have character 1. But character 1 could have the skin, the collision, or hitbox. That's a more popular term. And it might also have a gun, right? So the gun may also have modifiers like a laser scope or I don't know. I'm not very huge in gun games, so don't judge me. But you know, just an accessory or something. And this goes on forever, right? Same thing happens with character 2. I'm not gonna type all this stuff out again. But yeah, this is how it is. And then we have the level layout, right? Level layout, which could have like a million things, literally. A million. It just has so much to like fill with. So you know, the crossroad is a separate asset, the traffic lights are different assets as well. and then the pavement, the road, the cars that pass, the buildings in the background. They're typically all different sprites that we put in game. So effectively, this is a million children. Okay, so now we can look at execution. And the most important functions that are in the flow of execution. So here's init. Init is called when the object is created or instantiated. That's how we usually call the phenomenon. You also have ready. Now, this may be a bit tricky, right? Because init for initiation and ready feel the same. But they are actually for different events. If I go back into the script, I automatically generated this at the beginning of the lesson. And you can see the script. You don't have to understand what's happening here just yet. We are going to understand it. You see, here's ready. And here's a comment that says code when the node enters the scene tree for the first time. So let's assume we spawn a character in this scene tree, right? We may create the object, but only when it's assigned as a child does the ready fire. That's when it enters the scene tree. For the first time. That is important. Because you also have another function called enter tree, which fires anytime the node enters the scene tree. So this except always. So not just the first time of entering the tree. Because if you want to, let's say, switch levels, right? You may want to carry the characters through to another level, and that is a different scene tree, right? So the characters will need to leave the current scene and enter the new one. That would mean they enter the tree again, but it's they are already spawned, right? So the way I like to associate it is that, like, if the node spawned, that's when it becomes ready. If the object spawned, it is ready. If it enters the tree, however, or if the enter tree event is called, that may mean it has already been spawned, right? We also have exit tree, which is obvious, probably. This happens when we leave the tree. However, according to my previous example, this also happens when we enter a new scene because we need to leave this tree, right? To enter the new one. And that is in fact right. The next one on the list is code process. Now, the name of this is not quite obvious. In Unity it's called update, which makes more sense, but this executes every frame. You can read it here, code every frame. And also, you can just actually look these up because they're all here. Here's exit tree. And yeah, another interesting thing is that if the node has, it says if the node has children, its exit tree callback will be called last after all its children have left the tree. So why is that? Let's assume we have this situation, right, with the character. We are leaving the tree. And if we were to call the exit tree on character 1, these would not be called. Especially if like you're deleting the character, right? Or even if you just leave the tree, right? So at the moment of leaving, the children would also not be in the tree. They would be called orphans. That's actually the official term for when an object is outside the scene tree. So if the laser scope had a script that would maybe access the root for whatever reason, if it would want to do that, then it could not, because by the time the laser scope's exit tree is executed, character 1 has already done that. And when character 1 does it, this entire branch gets detached from the root. And so laser scope cannot access it. I hope that makes sense. So process executes every frame, right? Frame rate is dependent on your PC's performance and how heavy your game is. I guess that's obvious. We have physics process, which was the solution for inconsistent frame rates, because this executes 60 times per second. Imagine the scenario where you are moving a character to the right continuously every frame. Now, if you move the character in process, that's great. You will move, but if you run the same code on your grandmother's PC or like a low-end PC, the frame rate is going to be lower, right? And so they will move less. If you have 100 FPS, that means you're gonna move like 100 units. Let's assume that. But if you have 20, you will only move 20 units. So we have physics process, which runs 60 times per second. This is a 60 FPS function, you could say that. I'm pretty sure we can find it here as well in the documentation. No, it's not here. Oh yeah, physics process. Yeah, and if you're wondering, this is called physics process because the frame rate is synced to the frame rate of physics. Because, even in physics, it would be a disaster if the physics engine didn't have a fixed frame rate, right? Oh yeah, one other important function is input, which is called on an input. If you do an input. I guess this is obvious, right? Like even if you move your mouse, if you just do this, or if you use one of the mouse buttons or press a key, no matter what, input will be code. And then there are some more intricate built-in functions. We will look into them later on when we have a better understanding. But I think this is pretty much the first lesson. So yeah, that is the basics. It is actually a lot, so reviewing the VOD or the recording is advised because there's just a lot, really, a lot to process. Because especially for beginners, this is just a whole lot of information, and like there are books written on every topic we've covered, so one could talk about these for days, really. But if we get into the details too much, we will never finish. So yeah, this was the first part, and I'm hoping to see you the next time as well.